Vergence is a measurement. It measures the amount of spreading apart or coming together of the light rays coming from or heading to one single point. For instance, this picture, you see the light source, the point on the left, that's the sun, and the light rays coming from it are spreading apart, diverging, divergence. When you're working with vergence problems, you want to make sure that you always keep your light source on the left. Now, in real life, of course, the light source might be anywhere, but when you put it down on paper to work it out as a problem, wherever the light source is, flip it so that the light source is on the left. That'll be a lot easier for you to work out problems if you consistently do that. Here you have the light rays coming from the source, and they're spreading apart, moving apart as they travel. That's divergence. The light rays are diverging. And here you have the light rays coming from the light source and convergence into a point. I added the magnifying glass just to make it a little more authentic, because you wouldn't normally have the light rays do that without some sort of lens. When you're working with vergence problems, it's helpful to form a mental X where you have converging rays on the left and diverging rays on the right. The light source for the diverging rays will be just to the left of them or in the center of the X, and the light source for the converging rays will be to the far left of the X. It's also important to note that converging rays have what is known as positive vergence. Diverging rays have negative vergence. Now you can employ what I call the pointy end rule. Converging rays, the pointy end is on the right. For diverging rays, the pointy end is on the left. Now, keeping in mind that this only works if you do what I said and put the light source on the left. Sometimes you'll have something that looks more like this, where your light rays don't really make what you would think of as an X shape. It looks a little bit more like a diamond shape. So when you have this, which one is converging and which one is diverging? Well, the pointy end rule still applies, because we're not talking about which side of our picture converging rays or diverging rays are on. We're talking about which side is the pointy end, and as long as you keep the light source to the left, the pointy end of the diverging rays is going to be on the left, and the pointy end of the converging rays is going to be on the right. When light rays have traveled 20 feet, 6 meters or more, they become almost parallel. They really don't have any more vergence to speak of. We call it parallel rays, zero vergence, and this is called optical infinity. Optical infinity is from 20 feet, 6 meters or more away. Okay, I started off at the very beginning by saying that vergence is a measurement, and it is. So how do we explain vergence? Well, we explain it in terms of distance, and the unit of measure of vergence is the diopter. It turns out that vergence, the diopters, is inversely proportional to the distance from the point source to the observation point. Okay, what does that mean? You understand distance, you understand diopters. What is point source? What is observation point? Okay, the point source is probably the light source, and the observation point might be your eyeglass lens or the cornea of your eye. More than likely, the point source will be an object, like a tree, the object that you're looking at. The tree would be the point source, and then, or the light source, and your cornea, or your contact lens, or your eyeglass lens would be the observation point. Okay, so maybe you're thinking, what do you mean? How can the tree be my light source? How can that be the point source or the light source? Well, remember, we don't see objects. We see light reflecting off of objects. So the light might be coming from the sun, but it's hitting the tree, it's bouncing off of the tree, and it's reflecting towards you, the observer, or whatever the observation point is, if it's going to hit your eyeglass lens, your contact lens, or the lens of your eye first. That's still your light source. So this is how you would write your formula mathematically, what we just said. Vergence equals 1 over distance in meters. The meters part is very important. So if you have your distance in something else, it has to be converted into meters in order to equal diopters. Okay, I'm going to show you an easy way to picture this. We're going to draw the X. We're going to have our converging rays and our diverging rays. Our light source, of course, is on the left. And each of these rays, converging and diverging, are going to be 1 meter in length. 1 meter long for the converging rays, 1 meter long for the diverging rays. Okay, then we'll employ our formula. Vergence equals 1 over the distance in meters. Our distance is already in meters, 1 meter. So we don't have to do any converting from centimeters to meters. And that will equal 1 diopter. So I'm going to take my 1 diopter and I'm going to write it on the X. I'm going to put it up in the corner at that 1 meter length, plus on the converging side, minus on the diverging side. And there you have it. Okay, let's do another one. Let's do a distance of 1/2 meter. Okay, V equals 1 over 1/2 meter. Or you could put 0.5. If you have a half, you can invert and multiply and come out with 2, or you can use the calculator, however you want to work that out. But you end up with V equals 2 diopters. Then you put the plus 2 on the converging side and the minus 2 on the diverging side. And we can continue on and do 1/4 meter, or whatever distance you choose. It doesn't have to be half or quarter, it can be whatever distance you choose. So notice how as the distance gets smaller and smaller, or approaches 0, the distance on the bottom there, the power that we wrote on the top gets larger and larger as it approaches the center, it approaches infinity. That's inverse proportion. As one gets larger, the other gets smaller. Okay, these are the shapes that I'm using to represent convex and concave lenses. They don't all look like this in real life. In fact, they rarely look like this in real life, but a convex lens will have at least one side that bubbles out, and a concave will have at least one side that kind of curves inward. And I think of it as like a cave entrance. That's how I remember concave versus convex. A convex lens is a plus lens. It converges light rays, and it's used to correct hyperopia or farsightedness. A concave lens is a minus lens. It diverges the light rays, spreads them apart, and it's used to correct myopia or nearsightedness. Okay, now we can talk about focal points. There's a primary and a secondary focal point. Okay, the primary is where you need to place an object so that once the light rays come from that object through a lens, they emerge parallel. And the secondary is kind of, if you flip that around and you start out with parallel rays, the incident rays are parallel. Remember, incident means coming into the medium, in this case the lens. They start out parallel, and then the lens focuses them as we take a look at that. Here we have a convex lens and a concave lens. And you'll notice that we have conditions to determine the focal point because wherever these objects are placed, the light that's emerging after it goes through these lenses is parallel. Okay, so where is the focal point? Well, it's really easy to tell on the convex lens where that point is. But what about the concave lens? Well, with the concave lens, there really isn't one. Not a real one anyways. What you have to do is take these rays of light that begin converging until the concave lens diverges them enough to be parallel. You continue those out by drawing imaginary lines, converging them all the way to a point, and that's where you have your focal point. It's imaginary. It's virtual, it's called, not real. So in this instance, the convex lens has a real focal point. The concave lens has a virtual focal point. Virtual focal points are negative. Real focal points are positive. In this drawing, the light rays started out parallel until the convex lens converged them to a point, and the concave lens diverged them. So where is the secondary focal point? Well, I think you already know. And we're going to be working with focal length, which is just the distance in which the image forms in a plus lens or comes from in a minus lens. And don't get confused because we've been doing this with the vergence. If you look back in the pictures that we just looked at of the focal points, it's just converging and diverging, just like the vergence. Instead of point source, like we talked about in the vergence problems, we're using focal point. And instead of just distance in meters, we're using focal length in meters. And the units that we're looking for are diopters. It's basically the same thing. Focal length formula is D, or diopters, equals 1 over the focal length in meters. Just keep in mind that this 1 on top there, it is representative of the refractive index of air. If you're using a different medium, if you're trying to find a focal length and you're going through water or gelatin or something else, then you're going to have to use the refractive index of that material, that medium. Okay, look at the similarities between these two formulas, both measured in diopters. The reason for that is that the lens power is defined in terms of vergence. Or another way to say that is the power of the lens is how much it changes the vergence. A minute ago we talked about real and virtual focal points. Well, we can also have real and virtual objects and real and virtual images. And to explain this, we can use physics and some mathematics, but I'm not going to go into that right now, and I'm sure everyone appreciates that. I do want to kind of explain virtual, though, because I think it can be a confusing concept, but it's really not that confusing. Think of it this way. Pretend you're holding a mirror up in front of you and you're looking at your reflection in a mirror. And you can see through this mirror that behind you there's maybe, let's say there's a bouquet of flowers on the counter behind you, and you can see it through the mirror. Now, because you've looked in mirrors many, many times before, you know that that's behind you. Your brain is telling you that that's behind you, and it's not as small as it looks in the mirror. But if you've never looked, let's say you've never looked in a mirror, this is your first time, you might actually think that you can reach through that mirror, or you can walk through it, and because you can see stuff right there. You can see flowers out there in the distance through the mirror. So as you're looking into the mirror, those flowers are virtual. And the flowers that are behind you on the counter are real, they're really there, but the ones in the mirror aren't really there. What you do need to know in order to do calculations, you do need to memorize this: object, lens, image, in that order. Remember to keep your light source on the left, object, lens, image. If the object or the image is not on its correct side, if it's on the wrong side, then it's virtual. Now we're going to take the two formulas that we've been working with, the vergence and the focal length, and we're going to put them together into what's called the thin lens equation. Now bear with me as we work this out, because we're also going to use it, and it's going to be really cool. This is called the thin lens equation, and what this means is 1 over the focal length in meters equals 1 over, and d sub o means distance of from the object in meters, plus 1 over, and d sub I means distance from the image, and they're all in meters. And you're wondering, what does distance from the object and distance from the image mean? And you don't need to worry about it quite yet. We're going to go over that a little bit later, and you'll understand it by the time this video is over. And you can see how those two formulas that we were working with earlier play into this. 1 over f is actually the same thing as d, and 1 over the distance is actually the vergence. So we have vergence of the object, vergence of the image. And remember that d, v, and v are all in diopters, where our top equation we're working with meters, on the bottom we're working with diopters. Now you can see right off the bat that these variables are not going to work because there's too many v's. That's going to get confusing. So what we're going to do is we're actually going to replace the d and one of the v's with two other variables, two other letters. And what we're going to use is P in place of the D. P stands for the power, the lens power in diopters. And we're going to use U in place of our object vergence. And we're going to keep our image vergence at V. So we have P, U, and V. Okay, let's use this in real life, in a real life situation. It'll get a lot more interesting if we do that. Okay, we have a patient in the office, and this patient would like to be able to hold their book at about 25 centimeters away and be able to read it comfortably. Right now, the patient can't see it comfortably unless they hold the book out at 50 centimeters. Okay, this patient's a hyperope or a presbyope. So what this patient needs is an eyeglass lens that will make the book that they're going to hold at 25 centimeters look like it is actually 50 centimeters away so that they can see it. So the book that they're holding at 25 centimeters would be the object, and 50 centimeters away would be the image that we're trying to project. And here's a picture of that. Our book at 25 centimeters away is the object, and we want it to look like it's 50 centimeters away. That's our image. Okay, so we'll start out with this equation, the thin lens equation, and we don't know f. We do know that the distance from the actual object is 25 centimeters, and the distance that we want, the image distance, is 50 centimeters. Now look how we have that lined up. We have image, object, lens. Image is off sides, so it is virtual, making it negative. That's why we have a negative 50 centimeters there. We'll fill in the formula a little bit, and we get 1 over the focal length equals 1 over 25 centimeters plus 1 over negative 50 centimeters. If you remember arithmetic, you need to find a common denominator, which would be 50 centimeters, and then we're going to add 2 over 50 centimeters plus 1 over negative 50 centimeters, which is the same as saying 2 over 50 centimeters minus 1 over 50 centimeters, which leaves us with 1 over 50 centimeters. Now, we need our focal length in meters, not centimeters. So we're just going to convert that 50 centimeters to meters, which will leave us with 0.5 meters. So we know the focal length is 1/2 meter. So what do we do with that? Well, we still need to find out the lens power. So we use our formula D, which is the lens power or diopters, equals 1 over the focal length in meters. And we work that out and come up with our power is 2. So the patient needs a +2 lens. Or we can use our other formula, P equals U plus V. I've heard this referred to as the vergence equation. And remember, P equals the lens power, U equals object vergence, and V equals image vergence. So we don't know what the power is. That's what we're trying to find out, the power of the lens. For U, we need the object vergence, and if you remember, vergence equals 1 over the distance in meters. Well, we have the distance in centimeters, and we're going to keep it that way for the moment. So object vergence, U equals 1 over 25 centimeters is the distance of the object. And for image vergence, it is 1 over, and don't forget the negative because it's off size, it's virtual, that makes it negative. So we'll fill in the formula. P equals our value for U plus our value for V. And again, we're going to find a common denominator and add these two together. And we will come out with P equals 1 over 50 centimeters. Convert that to meters, making it P equals 1 over half a meter, or 2. I didn't convert it to meters right from the get-go because I thought it would be easier to work with using centimeters. So I did have to convert it to meters in the end there. So the patient, again, needs a +2 lens. Either way, either formula is fine, whatever's easier. It'll get the same result, obviously. Okay, this time we have a patient in the office, and the farthest point that this patient can see clearly is 50 centimeters away. Anything beyond 50 centimeters begins to get blurry. So this patient is nearsighted, myopic, and this patient will need a lens that will make objects far away at optical infinity look as though they're only 50 centimeters away in their farthest clear point, also known as the far point. So first we'll draw a picture, and we'll put our object at infinity. So anything in the distance, anything in it at infinity, we want to look like it's only 50 centimeters away. In other words, we want it to be clear for this patient. We're going to start by using the thin lens equation, and we don't know the focal length. We're going to place the object distance at infinity, and the image is offsides, so it's going to be negative, and it's 50 centimeters. We'll just fill in our formula with the values that we're using, and 1 over infinity is 0. So what we're left with is a focal length of minus 50 centimeters. When we convert that to meters, we have a negative half meter. And we're going to change that to diopters. So that's pretty easy. We come out with -2. The patient needs a -2 lens this time. Or we can use our vergence equation. We don't know P. P is the lens power. That's what we're trying to find out. Our object vergence is 1 over the distance to the object in meters. That's 1 over infinity. And our image vergence is 1 over 50 centimeters. That is virtual image, so it's going to be negative. And we'll fill in the formula. Our lens power equals our object vergence plus our image vergence. And our object vergence, 1 over infinity, equals 0. So we have our lens power at 1 over -50 centimeters. We're going to convert that to meters. And we have 1 over half a meter, negative half a meter. And when we divide 0.5 into 1, we get a -2. So the patient needs a -2 diopter lens. And that's about it for this video. Real quick though, kind of a disclaimer, I just wanted to say we're making some assumptions when we're working with these formulas. We're assuming first off that the lens is infinitely thin. We don't take into account the thickness of the lens. Also, we're assuming that all the light waves have the same refractive index in a material, which they do not, and we'll see that more when we work with prisms. And we're also assuming that the same medium is on each side of the lens, that's air. We're assuming that there's air on both sides. And that's it. Thanks for watching.